Yes, so thank you very much for the invitation. I'm giving this talk on seeing through space-time, the same topic that Günther Ullmann planned to speak about. And this work has been done in collaboration with Jaroslav Kurilev from University College London and Günther Ullmann from University of Washington and University of Helsinki. And so this is not so closely related to medical imaging, but there are some connections that I want to point out a little bit later, how one could use relativity, at least tools from relativity in medical imaging. Let me first recall some results from linear inverse problems. Namely, if you consider just wave equation or the corresponding equivalent inverse spectral problems, one could say that by using complex geometrical optics, one can apply this method of Nachman, Sylvester, and Ullmann for the inverse spectral problem for Schrödinger equation in Euclidean space. That would be in different formulation, that would solve an inverse problem for wave equation. Berishev and Kurilev, and using Tatarus unique continuous method, they considered an inverse problem of reconstruction of a manifold with a Riemannian metric. So that would be a wave equation with time-independent coefficients. And this method is very much based on unique continuous result for wave equation, and that holds only when all the coefficients are either time-independent or real analytic. And there are examples that show that the unique continuation fails for non-real analytic time-dependent coefficients. Grigory Eskin has used this boundary control method-like tools to consider inverse problem for a wave equation where the highest order terms are time-independent and the lower order terms may depend on time but are real analytic. In general, when you have a time-depending problem, I would like to somehow point out the difficulty that usually we are considering direct to Neumann mapping. For instance, here one measures this kind of like source to wave map on top of Earth. And when you have time-depending problem, then the question is, can you reconstruct the whole direct to Neumann mapping? Usually, you can only do once the measurement because the system is changing if it's not periodic. But there are possibilities to combine several measurements together to pack them together to one measurement. This was done by in the work that we did with Tapio Helin and Lauri Oksanen. So to study time-depending problems, the first thing is to study first the whole direct to Neumann mapping or the source to the wave map, and then look how to pack the measurements. So let me now go to nonlinear wave equations and time-depending equations. When things are time-depending, we can think this really as a Lorentzian problem of Lorentzian geometry. And typical examples from this comes from relativity theory and astronomy. So when you are looking telescope images in astronomy, there are examples like this. This is the Einstein cross. There's a gravitational lens that bends light so that there is actually one object on the other side. Light is coming, it's bending here, and you get here multiple images. And actually the time scales are quite huge. The time difference when you somehow have a sudden change here at the source, you see the light comes, there is different time delays with different roads. So the difference of time delays of this type of different images that you get can be even one year. So you should now think a problem where the time scales are measured so that the basic time unit would be like months, and like distances are with light years and so on. And there's also a possibility that instead of this type of multiple images, you get picture of Einstein ring that is here. So the question one would study in astronomy would be that you have looking somehow very dense set of stars, and there are quite many somehow changing stars. I will come a little bit later in this problem what type of data you could have. So there are actually stars are not so stable, they are slowly or fast varying. But to think on intuitive somehow problem. Let's consider the case when we have this type of like set of stars. We are looking very, very long time. There are lots of supernovas when you wait long enough, and you assume that you have like, you measure here and there supernovas. What you could say about the structure of space-time in this area? So let me define some concepts of Lorentzian geometry that are quite close to Riemannian geometry. Let us consider a manifold M that is the space-time. So you could think four-dimensional, 3 space dimensions, 1 time dimension. So we have a four-dimensional manifold, and then we have a Lorentzian metric, which means that you have a metric that is semi-definite. Here is, for instance, Minkowski metric. So if you think this as a matrix, one eigenvalue is negative, others are positive. Here is a picture of, you have a point here, and then you could think this as a Minkowski space. You look vectors here. Vectors on these light cones, they are called light-like. So they satisfy this condition, the metric of, like their length is 0 with respect to this metric. Vectors are time-like if they are pointing in these light cones. And all objects that has mass have to move with speed that is smaller than light. That means that they are moving along a curve in space-time that is time-like, which means that the tangent vector, the velocity vector for velocity of this curve is always time-like. We are also interested of finding conformal factor, conformal class of the metric, and I recall that two metric are conformal if there is a scalar that is a real valued positive function f, so that one metric, this matrix, is scalar function times the other metric. And changing conformal class of the light doesn't change, changing the conformal factor doesn't change the propagation of light at all. Then some more definitions. So here in this picture we have these light cones, light-like vectors, all vectors that are non-zero and length is 0. So they form these yellow cones in this picture. It has two components, the future light cone and the past light cone. And I denote by LQ plus the light cone at point Q that points to future. So that all future pointing light-like vectors. When you have this kind of supernova, it sends light to all directions in the future light cone. Then we have here a causal structure. We speak about, when we have a point of space-time, we speak about, here is like point P. Then we look, it's causal past, G plus of P. And similarly, all points that can be reached with a causal curve. Causal curves are curves that are either time-like or light-like. And similarly, we have the causal, here is causal past, like here. Causal future of point is here, J plus of P. Time goes here upwards. And the geodesic in this space-time by gamma, x is starting point, psi is starting direction. So this may be first non-trivial definition. We say that space-time is globally hyperbolic. This basically means that you can solve wave equation on it. If there are no closed causal curves, this basically means that you don't have time traveling. So you can't go to the future and return to the same time and moment. And then you assume that for any points, this kind of diamond-like offset. You take the one point, you look its past, you take other point, look its future, and then you look this diamond that you obtain. If these sets are always compact, then you say that the manifold is globally hyperbolic. This actually means that you can't, if you would somehow remove a point or area from here, then you could start from here, go with a causal curve to the boundary of the universe, and come back to here to the area that you have specified. So this basically means that you can't go and touch singularities. This is a cosmic censorship hypothesis. So this type of manifolds that satisfy these conditions are pretty regular. And you can factorize them so that you have a global time variable and space variable. So this is a product, this manifold, of real axis and three-dimensional manifold N that represents the space. And here you have a time-depending Riemannian metric. So this means what is the global hyperbolic structures. Let me explain very shortly what is the relationship of Lorentzian and Riemannian geometry. In Riemannian geometry you are looking at geodesics that are shortest paths between 2 points. In Lorentzian geometry you actually use proper time. You are moving along some curve in space-time. There would be a clock there on this curve, and you ask how much time passes, how much of passage of time the clock records. Here is the formula for it. You have a path nu. Here you compute basically the inner product of the velocity vector of mu with respect to metric g. You change that is negative. You change the sign and take square root. And this measures how much time passes when you go along this curve. So this is the analog of distance. And now in relativity theory, if you have 2 points so that z is in the path of x, then you look all paths that go from this point to here, and you try to find the longest path. The path so that you use as much time as possible when you are traveling from this point to this point. So you're not minimizing distances, you are now maximizing them. And so why you do this? Actually it would be very easy go from here to here with a path so that you don't spend any time. Namely, you would somehow take like a spaceship that you would travel with the speed of light so that you don't feel any passage of time. You would go a little bit, then you turn rapidly your direction like this and make this type of zigzag curve with speed of light. And no time is passing. So it is very easy to go from here to here with a path that has length 0. But to find the longest path, that is difficult. Anyhow, the maximizers, the longest paths, they are called geodesics in Lorentzian geometry, and they satisfy the same equation as geodesics in Riemannian geometry. So there are some similarities but some differences. For instance, this distance function satisfies the triangular inequality that is reversed. Okay, let me now go to inverse problem. Let me consider the data that we have. Let's somehow think this type of we could think a spaceship, or we are thinking that we have an observatory on Earth, and that is moving in space-time. So here is a time-like geodesic, or time-like curve, that corresponds to the route of our somehow observatory. And here we'll have 2 points, p minus and p plus, and we are looking in this set that is in past of this point, but not past in this point. So we are looking like this area. Then we have here some area of space-time. We could think that, okay, here is Earth, here could be like galaxy of Andromeda, and we wait so long time that we have lots of point sources here, like varying stars of supernovas. And when the supernova goes on here, then it produces light that goes in the future light cone. And then we assume that we record it in this neighborhood V, this blue set here, for instance of Earth here. So we say that here is a point Q in space-time. The light observation set is that we look light cone coming from this point Q, and we take its intersection with the neighborhood V of this set. So that would correspond to the case that you wait so long time that space-time is quite filled with supernovas, for instance, and then you somehow record the light that comes close to you. And you are asking, can you find the metric structure of this area of spacetime? So here is our result for the passive observations. Let's assume that we have a globally hyperbolic Lorentzian manifold of dimension at least 3. Then we have a curve mu here and its neighborhood v. And in this neighborhood we are observing all light observation sets corresponding to points that are here in this domain U. So we have the collection of all light observation sets corresponding to point Q, and Q is this set U here of the spacetime. Then this data here determine the set U, its topological and differentiable structures, and so up to change of coordinates, and also the conformal class of the metric, so metric up to a conformal factor in this domain. So what is the what are the ideas of the proof? Okay, here the set V where we do measurements. Here is a point, the Q, and then we observe light from here. So let's show that here is, for instance, like one light like geodesic that comes to this area. So let us point here, take a point and direction from here, and let's look this part of the light ray. And then we ask, what are all other points here? So here I have other points. Let's consider a point that is such that light that comes from here, from this Q prime, it coincides with this. If this is the case, the point has to be such that it is on the same light ray. So if the light rays for Q and Q prime coincides, then Q and Q prime has to be on the same geodesic. Now when I look this type of coordinates that I have put here, actually in 4-dimensional space I would put 4 geodesic. I ask that what is the time moments when I observe light first time from coming from point Q. This gives coordinates for point Q. And this construction here shows that actually in these coordinates that we construct using our measurements, we can see the images of light rays. So we can see lots of images of light rays. So at this point Q here, there in some abstract coordinates I can see lots of light rays. This gives me an open subset of the future light cone in these particular coordinates. Because the light cone is real analytic, knowing open set of the real, knowing an open subset of a real analytic surface determines the whole surface. So observations determine the whole light cone. So in this area, I can reconstruct all light cones. And this determines the metric up to a conformal transformation, so multiplication of the metric with a scalar function. Actually, there are lots of complications coming from the fact that in geometry we have conjugate points. In physics, when you look astronomical pictures, you have these Einstein rings. They correspond to this case when you somehow, here is a simulation in a wine glass, like here. You look a point source of light, and you are looking like this, the light source. And you can test it yourself. You see image like this. So you see this kind of Einstein ring type of structures in a wine glass. Please remember to empty the glass before you try this in the party. So now when you somehow having light observations with this kind of structures where you have this type of conjugate points, there are complications in the constructions. Then a few words about the applications. Actually, we often think stars as very static objects, but when you look at this kind of classifications, this Hertzsprung-Russell diagram of stars, so here is the spectral class and here is the magnitude. Here is, for instance, the main sequence, how the stars are somehow behaving. All these white areas here are varying stars. So actually, when you are somehow looking time scales of like months or years, you see variations that are like point sources. Of course, you also have supernovas that are somehow very clearly like point sources in space-time, but also there are all kind of like slave stars and other phenomena where you somehow have like stars that are somehow sending varying signals. So they could serve as sources in space-time. So here is, for instance, this kind of image. In this galaxy, there was a galaxy that in small area, you have recorded in some area very many supernovas. So there are also interesting areas of space where you have lots of supernovas. Then you can also somehow make a thought experiment. You would somehow consider light observations from a black hole where matter is falling to the black hole. You could ask that, this is just artistic impression, but somehow following here this picture, the light source is basically here. You could ask, could you somehow detect the structure of the space-time close to the black hole or system of black holes? At this moment, this is the best astronomical pictures, but maybe in the future telescopes may do better work than this on this type of events. Okay, let me go now from this kind of passive observations where you're just looking at the sky to active measurements, and this has some common points with medical imaging. For instance, in elastography, when you are doing that, you use in medical imaging, you actually send one elastic wave, an S-type of elastic share type elastic wave, and then you use a pressure wave to measure it. So this type of problem, say, you could actually formulate that you send a wave and you ask, can you use waves to image the propagation of the wave? And we are not using now this, we are not studying the elastography that would require study of elastic system, but we have started with this type of, we have started studies with Einstein equation and this type of simpler problem that is nonlinear wave equation. So let me now fix space and time dimensions so that we have one time dimension, 3 space dimensions, altogether 4 space-time dimensions. And then we consider nonlinear wave equation. So here we have just a standard wave operator with time varying metric of the speed of waves, and then I add here nonlinear term, function a of x that I assume that is positive everywhere, times square of u. Okay. Now we are interested of this type of geometry. Here's a geodesic. X is space-time, yes. We actually, yes, x here is x0, x1, x2, x3. And x0 is the time coordinate. So I have a geodesic in space-time. I take 2 points here and the neighborhood of this. Then I assume that I want to reconstruct maybe I draw this again. Geodesic, 2 points. I want to reconstruct space-time in this area when I do measurements in this area. So here in this area, I have sources that are these functions f's, and I record solution u, and I ask what is somehow the metric, or at least the conformal class of the metric in this area. So here's the formula of the wave equation in space-time coordinates. And we are considering the source to field or source to solution operator that maps the source f to the solution u in this set V. V is this neighborhood of one geodesic. Now we have nonlinear equation. So for small sources it has a solution. For large sources the equation may blow up. So we define this. This is nonlinear measurement operator now. It is defined on the neighborhood of 0 function, so for small sources. Our result is that we can actually use the previous result to create artificial, these kind of point sources or stars, you could, if you think astronomy, in this area. So when you know this blue area, this set V here, and you know the source to solution operator, this, to do measurements here, then you can reconstruct this area of the space-time up to change of coordinates. You can reconstruct this topology, its differentiable structure, and also the metric up to multiplication with the conformal factor. I want to emphasize that now in space-time, when you multiply the metric with the conformal factor f, the highest order terms of the wave equation are not changed. So this actually means that you can, for the wave equation, you can see the highest order terms, not the lower order terms, but the higher order terms. And also the geometry can be much more complicated. The topology of this type of domain can be quite complicated. Let me explain the idea of this. The idea of this result is that we use nonlinearity as a tool to help to solve the inverse problem. It is not some kind of perturbation term that you want to eliminate, but it is a term that you want to use to somehow get more from your data. So let us use this type of asymptotical expansion. Let us look to solutions that depend on epsilon, that is small parameter. So solution U, that is epsilon times W1. So this W1 is the solution of the linearized wave equation. Then you look like higher order terms. You substitute this representation to the nonlinear wave equation. And by Q, I denote here the inverse of the linear wave operator. Then I see that the W1 is just a solution of the linearized wave equation. W2 comes from this type of idea that the wave interacts with itself, produces a new source. The source produces a wave. You have third order interaction and fourth order interaction. And this type of terms we want to somehow use for our advantage. And actually, I want to present this for the wave equation because for Einstein equations, this is much more complicated. There are thousands of these type of terms if you compute everything. If you would compute everything by hand. Of course, there is some important terms, and most of them are not so important. So what we do? We actually send this kind of pieces of spherical waves or plane waves that propagate and then interact. And let's now change some coordinates of the space. Let's use just standard Minkowski space, but let's choose their new coordinate variables, xj's, such that this xj is 0, this plane is light-like. So that corresponds to this is a hyperplane, light-like hyperplane that corresponds to the growth of a plane wave. And then we look this type of plane waves. So this is just a positive part of function of a variable to power m. So we have somehow like the mth derivative of this function has a singularity that is propagating the space. So this type of waves are singular on hyperplanes. And how they interact? Two waves interact in the intersection of two planes. Three waves interact with the intersection of three planes. That is a line in four-dimensional space-time. So now when you have four-dimensional space, three lines, three plane waves intersect, they produce a line. And when four planes intersect, they produce point source in space-time. Now I use plane waves, but you could also use these kind of spherical waves that are produced at one point, and they propagate. We actually call them sails because they look like sails that would propagate in space. So how you analyze the interaction? You put this type of source depending on two epsilon variables. You solve out the wave equation and compute this derivative. This here gives this type of term that you have. So here is one source. Here is a linearized solution of the wave equation. You have two linearized solutions that interact, produce a source, and the source produces a wave. So this is wave caused by interaction of two plane waves. Then one looks at the geometry. This new source is singular on this surface, but this surface two-dimensional surface. When you look at this normal bundle, it has only light-like directions that are already normal in normal bundle of K1 or K2. So this means that actually this term produces no new propagating singularities. So it's quite boring terms. So two-wave interactions doesn't give anything interesting. Oops, let me just go here. So three waves, when they interact, then you actually have like three waves, three planes intersect. They produce in space-time a line like this. So this is now in the space-time. Space-time line means actually that you have a point source that is propagating to the future. And actually this point source that appears to be somehow created, it is a point source that seems to move faster than speed of light. So it produces a little bit like in this kind of like when you somehow are looking like ultrasonic, hypersonic like planes, you create, or this is a bullet going in air, it produces this type of shock wave. Now we don't have shock waves, but we have a wave which geometry is very similar to this here. Let me show here a video on this. So here are now three, this is a snapshot of given time moment. Three plane waves start to propagate in space. So this is not simulation of the wave equation, this is just simulation of the geometry. Okay, now I start them. Now they start to propagate. They propagate, they start to interact. When the interaction happens, nothing interesting yet happens. But when all three waves collide together, they produce a point source that starts to move into space, and that causes a conic wave that starts to propagate to some directions. So that would be very interesting. We see somehow new waves coming from this kind of line of space-time. But who knows, the waves that we have produced somewhere here, they might somehow propagate and we will never see them. So that's why we have to look actually, we have to consider fourth order interaction. So I consider four sources. I have here several sources, four of them. They send waves. This is the space-time picture. Here is time. Here is x prime in R3. So they collide here and produce a new source. So we look this type of sources. We solve the wave equation, get the solution, differentiate with respect of epsilons, evaluate this when all epsilons are 0, and then we see that we have now four plane waves that have interacted. So we have four waves that intersect in space-time. The intersection is a point. So when I look at where this is singular, this fourth order, so the wave that has been produced by fourth order interaction, that is singular in a set that contains all these plane waves. It contains these conic waves, and then there is a light cone from a single set of space-time, single point of space-time. And this is what we are somehow very interested in. Let me show this as a video. And now I have four planes that plane waves that start to propagate. This is again simulation of the geometry. Okay, the waves start to propagate. Two interactions started. Nothing interesting happens. Three interactions start to happen. There is this kind of conic wave. Four plane waves interacted at one point of space-time, and that produces a source on space-time that produces a spherical wave that starts to go to all directions. Let me run this again. Okay, so waves propagate, interaction starts to happen. Soon 3 interactions start to happen. Now all 4 waves intersect in one point of space-time that produces a space-time source that sends a wave to all directions. This is what we see to go to all directions. So this means that by using this kind of, these are very lucky, all this, we somehow consider this type of geodesics that somehow go into space-time. If all of them intersect, then this kind of plane waves that are propagating close to the geodesics, they interact here in such a way that we produce like an artificial point source, artificial star in the space-time that start to send wave to all directions. And because it goes to all directions, it returns to the area where we do our measurements. So then we can find this, our point of light observation sets that we used in this passive observation part of this talk. So now we don't have somehow sources in the space-time. We produce them by using wave equation. We are making observation of this type of sets, and they determine the structure of the space-time and metric up to a conformal multiplication of the metric by scalar function in this kind of diamond-like of set where wave can propagate and the information can return. So we also have applied this for Einstein equations. You could ask this kind of like thought. You can now make mostly thought experiments. You said that you assume that you are living in this type of strange space-time where you have this kind of like wormhole. You do measurements here. Could you somehow detect the structure of the space-time in this area? So how this is related, how Einstein equations are related to this nonlinear wave equation? Einstein equations are like here. The Einstein tensor that is computed by using the Ricci curvature. So it's just some curvature tensors of the metric that is equal to T. And T is the stress energy tensor of the matter. In vacuum it is 0. If you add some matter, that we do a little bit later, this changes. But the Einstein equation here, when you write it in right coordinates, so in so-called wave map coordinates or in wave gauge, that produces this type of nonlinear wave equation. So here we have a wave operator for the metric tensor G, and this metric depends on the solution. So it is the same tensor, or actually it's inverse. And then there is a lower order nonlinear perturbation. And then there's extra difficulty that the Einstein equation doesn't produce only this equation, but it produces also one extra condition. So the divergence of the stress energy tensor has to be 0. This has to be satisfied so that the solutions are physically relevant. So we get from Einstein equation nonlinear wave equation, and also one extra differential equation. This basically somehow could be interpreted that in now very, very rough terms, that the total energy of universe is conserved. So how you could somehow formulate inverse problem for this? You have to add some matter equations for some like electromagnetism or something else, so that you can implement measurements. In vacuum, you can't somehow speak about measurements, because the Einstein system is deterministic. Nothing is changing if you don't do any changes. So we chose the simplest possible matter model instead of electromagnetism, which shows the scalar field. So this corresponds to a spinless particle, and we add here sources. And then in relativity theory there is a standard coupling term, how a scalar field and the metric of the space-time are coupled together, and it is here. And physicists actually say that this equation, interpretation is this, that this equation tells that, okay, the matter fields tell to the space how to curve, and then the metric tensor, the space, tells to the matter how to behave. And then we have added here some extra source terms that correspond to some other physical fields. And to obtain physically meaningful models, we need to have this physical conservation law to be satisfied. And this is actually the difficulty now of somehow speaking about somehow this kind of like source to solution operator or any kind of measurement operator. Because so we need to have this type, the sources have to satisfy these sources, they have to satisfy this differential equation so that they are physically meaningful. And here this depends on the solution. So the sources that you are allowed to use, they depend on the solution. This makes so the formulation of active measurements in relativity complicated. Okay, what we can do, we can show that if this type of condition is valid, and we consider particular matrix, if this matrix is invertible, then we can take the conservation law and one extra equation to obtain 5 pointwise equations that we can solve at each point. So we can somehow find lots of sources for which we force conservation law to be valid. This condition could be could be interpreted in such a way that we say that if the background fields vary enough, so if there is enough variation of the background fields, then they contain so much energy that you could take the energy from these background fields to implement the measurements in such a way that for stress energy tensor we can add any term, and then we construct a source for the scalar fields that corresponds to that is like a negative source that okay, how to say? So we could say that we implement source F1, this takes some energy, and then we use other source to compensate the energy that we needed to implement this source F1. The abstract property that actually is somehow holding here is that we have some kind of like micro linearization stability result, but maybe I don't go to this. I just go to the final result. So the final result is that if this condition A is valid, so the background fields vary enough, then we can construct lots of sources in this green area, so that if we have the data that corresponds to these collections of the measurement domain, the metric on it, then the physical fields in this area and the sources in this field, and we consider only this type of like pairs of solution and sources so that this conservation law is valid, then we get enough information to determine the topology and the differentiable trajectory of this diamond area and the metric up to a conformal change. Thank you very much for your attention.
Is it possible to supplement your original nonlinear wave equation model with subcoupling between A and F so that you have an additional conservation law to mimic the situation with the Einstein problem?
So for the A and
understood well. In the Einstein model, you have this additional compatibility condition satisfied.
Yes.
Can you go back to your nonlinear wave problem and modify it appropriately so you have a simpler model?
Yes.
By doing some coupling between A and F. This probably will teach you something.
I see. Yes.
In other words, your model did not have one essential feature of the Einstein model, namely the existence of this additional conservation law. So my question is, can you modify your model problem in such a way as to include this additional conservation?
It's actually, yes, when we study the Einstein equation, we do very much like this thing that you suggest, that we add there a function, this kind of like adaptive source functions, that we would think somehow that they actually are models for the measurement devices. They are actually pretty complicated, but of course the physical model for measurement devices that you use to implement the measurement, those are quite complicated. So that's what we actually do, is that we take this nonlinear equation, and then we add their adaptive source functions.
Another question, yes?
In the case of wave equation, your nonlinearity is u squared.
Yes?
What kind of justification is for u squared?
Yes, so actually that is actually more like a toy problem. I mean, actually you could study this, so for the Einstein, so for the Einstein equation, the nonlinearity is much more like complicated. It's like here. So, but you have to. We use this wave equation just for simplicity. It is basically but you could somehow put there also no other type of nonlinearity. But then you should use these tools. But you somehow verify that the nonlinearity is such that actually this type of that the nonlinearity is such that all the nonlinear interactions that are caused, that by chance they don't cancel each other. So you need to know that actually that there are no two like equally strong nonlinear terms that could with very bad luck could cancel each other. But I mean each type of nonlinear equation needs new type of considerations. Yeah.
So you said that nonlinearity helps you to solve.
Yes.
What happens if you replace u squared by u to power 4? Will it be better or worse?
Actually, this u to power 4 would be better, yes. U to power 3 would be difficult.
Any other question? Okay, let's thank Matti again.